Hi, my name's Peter Shawn. I'm a professor here at the University of Maryland. And today I'm going to be demonstrating our Shive wave machine. So this is a demonstration that we have that shows the wave propagation. If you've studied wave phenomena, you know that waves travel in a medium. And in the medium, there are different masses that are connected together with something spring-like. That's basically what gives you a wave. In this device, the Shive wave machine has a wire along the center, and it has these crossbars that are soldered to the wire. So each one the wire can twist, and so this forms a torsional spring. And that links each crossbar to its neighbor with something springy. So it serves as the masses and the springs for the system. Also, these bars are not going to translate, but they're going to rotate. And so it's really the rotational inertia, or the moment of inertia, that serves the role of mass in this setup. So we've got torsional spring and rotating masses. Anyway, putting that all together, since each rod is connected to its neighbor, if I shake this rod at the end, that motion will get transferred in some way to its neighbor. So let's see what happens if I do that. All right, so you can see that it launches a wave. And then, in fact, the wave reflects back from the end. And that's one thing that can happen with waves. This medium just ends suddenly here. This last rod isn't connected to anything. But because it doesn't have a continuation of rods, it has to change, and that energy has to go somewhere. And the energy ends up reflecting backwards like this. If you looked closely, you saw that the reflection was just kind of like a mirror reflection. I made a downward dip, and then when it reflected back, it was also a downward dip. OK, so we've seen one wave. Let me change things now. I'm going to take this clip and just clip this rod at the end. So that rod now can't rotate. It's fixed. And so I've changed the boundary condition, the condition of what happens at the edge of this wave medium here. So now what do you think is going to happen if I launch a wave, if I launch the same kind of wave? Does the wave just stop there? Or does it still reflect? Let's see. Aha, it still reflects, but now it reflects differently. So if you saw that, I made a downward dip, and when it got here, the reflected wave was upward. All right. But each time when the wave reflects, it's reflecting with the same speed. So that speed is a property of this wave medium. And it's controlled by the twistiness of the wire, the torsional spring constant of the wire, and it's controlled by the moment of inertia of these rods here. So if we look over at this other device, this has the same wire in the middle, but it has shorter rods. So what do you think is going to be different about this wave machine? Exactly the same? No. It's going to be different. The way the spring and the mass, or in this case the torsional spring and the moment of inertia combine, that gives us what's called the impedance of the wave medium. This has, and the impedance, a larger mass is a larger impedance, so a larger rotational inertia is also a larger impedance. So this has a higher impedance than this machine. And let's see what that does to wave speed. OK, so we're seeing that this machine with a smaller impedance has a faster wave. We can also hook these together and see some interesting things. So let me line them up and clip these wires together. So now a twist in one wire will get transferred over to the other one. Let's see what happens. So pay attention to the speed, and then let's pay attention to any kind of transfer there. OK, so in fact, it does transfer the wave. And you can kind of see that it launched the wave rapidly. The wave speed is a function of the medium. So the wave that gets transferred then travels faster in this medium than it did over here. I can do it in the opposite direction. You can maybe see that too. So I'm going to launch the fast wave in this medium. And that gives us a nice slow wave over there. And the other thing you might have noticed is that there is a reflection in the first medium. So let's do that again. Let me make my downward dip on this side. And we got a reflection that was downward here, although weaker than we got originally when this was disconnected. So this is going from high impedance to lower impedance, and we got a reflection in the same direction, which is a special case, a general case of the special case when I had this totally unconnected. A rod that's free to move has a zero impedance. So there it was going from the impedance of this medium to 0, and we got a strong reflection. Here it's going from the impedance of this to a smaller impedance, and we get a smaller reflection. If I launch the wave from the other end, then let's see what happens. OK. That was a downward dip, and it transferred a downward dip wave into that machine, but then there was a reflection here, and that reflection was upward, a little bit weaker. So this is going from a low impedance to a higher impedance, and that makes a reflection that switches signs. Clipping this rod is then a special case of an infinite impedance. And so when I just had the one machine with the clipped end, it was going from the impedance of the medium to infinite impedance, and we got that inverted reflection coming back. OK, I'm going to leave you with one last wave.